Hi everyone, good morning. Do you guys hear my voice? No? Okay, that's weird. So now, do you guys hear my voice? All right, yeah, thank you. So last time, we are talking about some basic stuff about probability theory and statistics theory. So today we are going to finish that review part, and hopefully as soon as possible we are going to start talking about regression analysis with one single random regressor. Okay, so last time when we construct this kind of statistic, so here we have underlying distribution, and from that distribution we have a random sample of size n. And so once we have random sample, then it is straightforward to calculate the sample average. So y bar sub n denotes the sample average. And the standard error of the sample average, we had a formula for the standard error of the sample average, right? So if we know the underlying population mean, then we can calculate this ratio. And for some historical reason, this ratio is called the T ratio, because under some additional assumption, this ratio is exactly distributed as T distribution. But in this course, because we don't trust that assumptions, we are not going to use T distribution at all. But fortunately, under weaker condition, as long as sample size is large, then this ratio turns out to be distributed as a standard normal distribution. So here we have very interesting example. So underlying distribution is a Bernoulli distribution. So Bernoulli distribution is a distribution for binary random variable. It takes value 1 with some probability. So in this example, the probability is set to be 0.78. And otherwise, the random variable is 0. So it takes value 1 or 0, and everything else is impossible. So from this very simple distribution, this is very simple, and also this is very different from normal distribution. So from this underlying distribution, we draw a sample of size 2, and then we construct the distribution. Because it is a discrete random variable, it takes only 2 possible values. When we have sample of size 2, the average can take 3 values. 1 over here, 0, and 1 over here, 0.5, and 1 over here, 1. But because we have to divide this difference by this scaling factor, the number is not exactly 0, 1, and 0.5. This is a scaled version. So anyway, the point is here, when we take this ratio, the true distribution looks like this histogram, right? So this is very different from normal distribution. Now we increase the sample size to 5. Now we observe 5 random variables from the same distribution over here, and we take the sample average and constructed the sampling distribution of this ratio. It looks a lot more similar to the normal distribution, but still very different. Now sample size is 25. Oh, the sample size is 25 is this is really, really small sample size compared to the average sample size that we are going to look at in this course. However, even when we have only 25 sample, the distribution of this ratio, the T ratio, is now very similar to normal distribution. When we increase the sample size to 100, now we really can use standard normal distribution to approximate the distribution of this T ratio. Okay, so using this fact, this is a statistical result. Using this approximate result, we can construct hypothesis. We can conduct a hypothesis testing and construct confidence interval. So before doing that, we were reviewing some properties of the standard normal distribution. So we discussed about this slide, and actually we covered this one and that one, and here we covered up to here during the last lecture, right? So I'm not going to go over the same thing again. However, let me give you some graphical representation of the standard normal distribution and also graphical explanation of what we are doing here. So let me turn on this one because I want to draw something. Okay, right? Do you hear me? Okay. Yeah, it looks like microphone is off now. All right. So standard normal distribution. I assume everyone here knows how to draw the standard normal distribution, right? So basically, suppose we have random variable z. Do you see? Yeah, let me make it a little bit bigger. So z, and say this is distributed as normal distribution with mean 0 and the variance 1. If variance is 1, then that means the standard deviation is also 1 because standard deviation is just square root of n. Now, let's forget about sampling and, the t ratio, things like that. Just focus on the property of standard normal distribution. In history, there are so many smart statisticians and probability theorists. They figured out everything about this simple distribution. Turns out that the shape is centered around 0. Okay, and the shape looks like bell shape like this. I wish to be able to do a better job, but trust me, this is my best. Okay, so the shape is symmetric about 0. So, this is just, my work. So maybe you might argue that the left-hand side is not exactly the mirror image of the right side, but this is supposed to be mirror image. Okay, so now for some reason we want to look at some tail probability. So here, whenever you have probability density function, by the way, this is the shape of probability density function of this distribution, standard normal distribution. Okay. Okay. Now, for some reason that we are going to use later, we want to look at this tail probability. When you have graph of probability distribution, then the probability of random variable is just the area under the curve, area under the graph. So for example, if this number is 1.96, then the random variable z is greater than 1.96 is 2.5. We know this. We know this from statistic theory. And also, because the density function is mirror image, we know that the probability that the random variable is below negative 1.96 is the same as this probability. So this is also 2.5%. Right? Okay. All right. So most of the time, this random variable will be between negative 1.96 and positive 1.96. So this random variable will be between this interval with probability of 95% because it is going to be bigger than this point with probability of 2.5% and smaller than this point with probability of 2.5%. So, obviously, probability sums to 1. So, therefore, this random variable will be between these 2 points with very large probability. In this case, that is 95%. So mathematically, we can say that probability that random variable z is less than 1.96 in absolute value is 95%. And the other probability, the z, is greater than 1.96 is 5%. Okay, so we have these expressions in our slides, in our lecture note. So you don't really have to write down this again. So what we argued last time is this event that the random variable is between these 2 points, these 2 cutoff points, is very likely it's 95%. And the other probability, the other event, the random variable is greater than 1.96 in absolute value is very small. So we can say that this event is unlikely, right? So here, the situation is we know for sure that this random variable is normally distributed with mean 0 and variance 1. However, now we need to refresh our memory about the sampling problem. So let me lower this paper a little bit. And we had this estimation problem. We have random sample that is IID. What was IID? Identically, independently distributed as some distribution, but we don't know what that distribution is. So last time we used something like this, P. I made it a little bit stylized because this is a population, so I want to have some some distinguishable notation. But anyway, this doesn't matter. So only thing we know is expectation of each one of them is some fixed number mu. This is obvious result because they are all coming from the same distribution. Therefore, obviously, their expectation has to be the same. But we don't know what this is. And the variance of it is sigma square. But we don't know what that is. And in ideal situation, probably no, I'm sorry. This is not an ideal situation. But if you're really challenging, then probably you might want to uncover, learn everything about the population distribution. But that's not what we want to do. What we want to do is we just want to estimate this population mean. Okay, so population mean using random sample of size n. So our estimator is just a sample average. I'm not going to write down the formula for this sample average. Why? Because this is just average. And also we can calculate standard error of this estimator. And if we know the deviation from the population mean, which we don't know yet. And if we divide this deviation by the sample standard error, then turns out that this is approximately distributed as what? Standard normal distribution. So now we can repeat the same thing we did here using this ratio instead of z here, right? So let me do it just quickly. So we have standard normal distribution that looks like this. And that is centered around 0. And for some reason, we want to look at these 2 cutoff points. One is 1.96, and the other one is negative 1.96. That is because the probability that standard normal random variable is greater than this point is 2.5%, and less than this point is also 2.95%. Okay, so this ratio has this distribution approximately. That holds only when sample size is large enough. All right, now we know that this ratio is approximately distributed as this bell-shaped, very nice distribution, but this is true only when we know the population mean, the value of mu here. Okay? But the problem is that we don't know what that is. That's why we want to look at hypothesis. So, this is really abstract. This is a simple example, but this is really abstract example in the sense that we can we haven't defined what these random variables are exactly yet. So we can develop many different examples using the same notation here. So suppose we are interested in tossing a coin, right? Then y1 to yn, these are all binary random variable that takes value 0 or 1, and everything else is impossible because the random variable y is going to be indicator for the experimental outcome that we see head instead of tail. If the outcome is tail, then the random variable takes 0. Okay? So that is one possible example that we can apply. In that case, our hypothesis should be population mean is going to be 0.5 because we believe that when you toss a coin, with half probability, the outcome is going to be head, and half probability, the outcome is tail. But we can use this example for many different kind of situations. So, in any case, suppose we believe some theory that is summarized by this hypothesis. So, under our theory, we believe that the true value of mu is some number. In toss coin example, this number mu naught, mu superscript 0, mu naught is 0.5, but it doesn't have to be 0.5. It may depend on the application, the problem that you have. Okay, then under this null hypothesis, what I mean by under the null hypothesis is if the null hypothesis is true. If the null hypothesis is really true, then we can say that this ratio is normally distributed approximately when sample size is large enough, right? So we can apply the same argument for this graph. The probability of these two tails is only 2.5%. Therefore, it's unlikely event. Otherwise, this ratio is going to be between this interval with large probability that is 95%. But now we know that this mu naught, this value is our hypothesis. We don't know whether this is really true or not. And actually, the reason why we construct this ratio is because using this statistical result, we want to test whether this hypothesis is right or not. Okay, so then, given that we are not sure about this value, this hypothesized value, if this number is too small or too large, then we may suspect the validity of our theory. If this ratio is around 0, quite close to 0, then that is a likely event, and we don't have strong reason to reject. we don't have a strong reason to say that this hypothesis is wrong. But if this ratio is too large, too small, or too large, then we can interpret it as a strong statistical evidence that is against the validity of our null hypothesis. So we want to reject the null hypothesis. Okay, so that is our decision making. Whenever this ratio is greater than 1.96 or smaller than negative 1.96, we reject the null hypothesis because we believe that under the null hypothesis, if the null hypothesis is true, then such a large number or such a small number is unlikely. So we interpret it as a strong evidence against the null hypothesis. However, even if the null hypothesis is true, because this is a random variable, it's possible that the ratio is greater than 1.96 or smaller than negative 1.96. So in that case, if the null is right, we are making a mistake. This mistake, is inevitable because our decision rule is just reject the null hypothesis whenever this two-tail probability becomes relevant. But these two-tail probabilities, these two-tail events are possible, still likely, even when the null hypothesis is right. So this kind of error, we are mistakenly rejecting the null hypothesis when the null is right. This mistake is called type 1 error probability, type 1 error. And in that case, the error probability is, as you see over here, 0.5% plus 0.5%, therefore it is 5%. And this error probability is called level. You can find it in the slide. So level of the test or size of the test. Sometimes people say that it's a significance level of the test. So the level is basically probability of making type 1 error. All right, so we stopped here last time, and let me so here we're going to reject the null hypothesis at 5% significance level. So we are scientists. People are making decisions. Every day our life is full of decision makings. So as a econometrician or statistician, here this is a very important decision making. Based on our sample evidence, we make this decision. We reject the null hypothesis. But because we are scientists, we have to admit that this decision making is subject to some possible error. And that error arises 5% of time. So we have to admit that this decision can be wrong. And scientifically, we can give the number. The likelihood of this error is 5%. That is what we mean by we are rejecting the null hypothesis at 5% level. Okay, so and we are going to do this very often. So 5% is the size that's been chosen in the literature by so many people, very popular for some reason. Maybe this 5, this is a nice number. So that's why people are using this. And also this is small enough. But you don't really have to use 5. If you want to be more conservative, you want to reject the null hypothesis only when you have much stronger statistical evidence, then you can be more conservative. So in that case, your level will be smaller. So another widely used number for level is 1%. Of course, if the level is 1%, then the critical value is going to be different. The critical value is not 1.96 anymore. This 2.576 is the critical value for hypothesis testing with size of 1%. So decision rule is going to be similar, but a little bit different. When the ratio is greater than this critical value, you reject the null hypothesis. So as you see over here, level is not a fixed number. That is different for each person, each statistician. When you are doing your own research, you have total freedom of choosing the size of your hypothesis testing. Typically, you're going to choose 5% because everyone else is doing it. And if you are a more conservative person, if you really believe the null hypothesis is really true, then you're gonna use smaller number for the level. Like in that case, that is 1%. Or some people can use 0.1%. That's up to you. So there's some tricky part regarding this issue. You write a paper, and there are so many different readers. So the readers are going to read your report, your research paper. And if you report only the statistic, this t ratio, then, sorry. So if you say you're going to reject the null hypothesis, for example, you're going to reject the null hypothesis at significance level of 5%, then it's like you are forcing all your readers to have the same level, right? You're going to choose the level, and there's no guarantee that your readers will have exactly the same level that you choose. So, what I want to say is everybody, all the readers may have different level because, they might be more conservative or less conservative. They may believe the null hypothesis more strongly than you guys, or they might have bigger doubt about the null hypothesis. So it should be nice if you let your readers to conduct hypothesis testing using their own level. So one way to do that is reporting p-value. So I'm not going to go into detail about the p-value because we need to do some mathematical things. But fortunately, many statistical softwares are reporting p-value as default. So when you run regression later, then on the computer output, you can easily find the p-value of the estimation inference exercise. So once you have p-value, then no matter what your level is, you're going to reject the null hypothesis. The p-value is smaller than your level. So this is another decision rule. So this is much more convenient, especially when you don't know what is the right level for your audience, for your readers. So instead of reporting that you're going to reject the null hypothesis because of blah, 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 you can just give this one number, p-value, then your readers can do their own hypothesis testing using this number, p-value, because they're going to have their own significance level. And when this p-value is smaller than their significance level, then they're going to reject the null hypothesis. So it is always desirable to report p-value instead of reporting your own hypothesis testing result. Okay? So p-value is one way to conduct hypothesis testing. And another alternative way is to construct confidence interval. So confidence interval is closely related to hypothesis testing in the following sense. If your level if your significance level is 5%, then the relevant associate confidence interval is 95%. You're smart, right? So whenever it is 5%, then you need to have 100 minus the significance level percent confidence interval, right? So if you have 1% of significance level, then the confidence level for your hypothesis testing is 99% confidence interval. Okay? And the formula is very simple. Actually, this formula comes directly coming from this expression. If you are interested, then you can derive, using this result, you can derive the formula for confidence interval, but I am not going to do that. This is not a difficult job, but this is just a review, so I'm not going to do that. So, however, you know, the formula is so easy to remember. You have sample, average, and plus minus 1.96 times standard error. That's it. If level is 5%. So this is the this is formula for 95% confidence interval. If your level is 1%, you need to consider 99% confidence interval, and the formula is just like this, very similar to the one before, but you have to use different critical number, critical value. So the decision rule is just this. If the value under null hypothesis is outside the confidence interval, then you're going to reject the null hypothesis. So simple. In other words, the confidence interval is the set of parameter values that cannot be rejected by two-side hypothesis testing with given level of significance. In this course, we're gonna repeat this kind of exercise in a different situation many times. So here, the application is just, estimation of population mean using random sample. Later, we're gonna construct, actually today, we're gonna construct OLS estimator. And for the OLS estimator, we will do something like this: estimation and the hypothesis testing and confidence interval, just like this. We start the OLS estimator with a single random variable, single regressor, and later we're gonna expand our analysis toward situation where we have more than one regressors. We will do the same, in the sense that we will estimate some parameter, and then we will conduct hypothesis testing, and we will consider confidence interval. So that is why we are reviewing this basic stuff from statistics theory. So this confidence interval formula is so easy. 1.96 is the number that you should keep in your mind, because you're going to use it many times. 2.576 or 2.58. It's not very difficult to remember this number, so I encourage you to remember this number. But even if you can't, for some reason, that's okay, because for your exam, I'm going to give you these numbers in some form. I'm not going to provide the entire probability table of standard normal distribution, because that's a waste of space and waste of paper, because we're going to use only these two numbers. Okay? All right. Let me emphasize just once again. The right interpretation of confidence interval is the set of parameter values that cannot be rejected by a two-sided test of significance level of alpha. And whenever you have alpha significance level, the associated confidence interval is 1 minus alpha times 100% confidence interval. Some people interpret confidence interval in a different way. When you have 95% confidence interval, some people often say that the true parameter value is included in this confidence interval with a probability of 95%. I guess you guys may be familiar with this interpretation. Let me repeat it again. Many applied people, especially not theorists, applied people often say that our 95 confidence interval contains true population parameter value with 95% probability. It looks similar, but this interpretation is technically wrong. And many people have this wrong interpretation. This last bullet point is the right interpretation. Actually, I know where that wrong interpretation comes from. We are going to get to that point later, not today. Because we have to discuss about repeated sampling. That is a little bit more complicated concept. So I don't want to do that right now. But for now, for you guys, it is safer to have this last bullet point as correct interpretation of confidence interval. All right. So now, until now, we had a situation where we have one random variable or set of random variables that are coming from the same distribution. Now let's extend the situation a little bit, just a little bit. Instead of one random variable, let's say we have two different random variables. And they are somehow related with each other. So we want to measure their statistical probabilistic relationship. Say we have x and y random variables, two random variables, and one way to measure their relationship is to compute this covariance. And the formal definition of covariance looks like this. So let's look at this inside thing. The first parenthesis is deviation of random variable x from its population mean, and similarly for the second random variable y. So this second parenthesis is deviation of random variable y from its population mean, and this outside expectation takes overall central tendency of the product of these two deviations. So whenever this deviation is positive, say this is also positive with a high probability, then this expectation is positive. So if covariance is positive, then we can say that x and y are moving in the same direction with more probability. Okay? Using similar argument, whenever this deviation is positive, more likely y, this second deviation is negative. Then that says that whenever x is increasing, y tends to decrease. So obviously, this covariance is negative. So when those two random variables are moving the opposite direction, it's not a deterministic relationship. Sometimes they are moving to the same direction, but it is more likely that they're moving the opposite direction. And then the covariance is negative. So you compute covariance, and you can say that whether they are negatively related or positively related. But one serious problem of a covariance coefficient is that it depends on the unit of the random variable, unit. So suppose x is, so here I put it in the footnote. So X is household income, and Y, say Y is household consumption, right? If you are making more money, then probably you're going to spend more money. So presumably X and Y are positively correlated. Income and consumption are money values. So we have measure unit for those money value. Usually we are using dollar in Australia, right? So using dollar, we measure these two random variables, and then we take the covariance, and we found some number. But for the same thing, we can change the unit of the measure to cent instead of dollar. Then turns out that the covariance measured by dollar is much smaller than the covariance measured in cent. Especially the second covariance. The covariance measured in cent is 10,000 times bigger than the covariance that is measured in dollar. So covariance is sensitive to the choice of the unit. So when we have large covariance, we cannot say the relationship is very strong, because it might be the case that we are using different unit. We are using cent instead of dollar, right? So it will be nice if we have measure for relationship that doesn't depend on the unit, the choice of unit. So that is what this correlation coefficient is doing. The formula looks like this, and this formula comes from this relationship. Covariance in absolute value cannot be greater than the product of two standard deviation. So we divide the covariance by the product of standard deviation, then this ratio cannot be greater than 1 in absolute value. So it has to be between -1 and +1. If it is 0, then that should be the case that covariance is 0. So there's no correlation between X and Y. If it is 1, exactly 1, then there's a deterministic relationship between X and Y. And the relationship is positive. And if it's -1, the relationship is deterministic again, but the relationship is negative. Okay, so here, let me give you some examples. If X and Y are independent, then covariance is 0. Therefore, correlation is also 0. But even if covariance is 0, those two can be dependent with each other. So here we have such an example as well. So by the way, we have 4 pairs of random variables, X and Y. So this is an example of positively correlated random variables. And this is the example of negatively correlated random variables. Correlation coefficient is -0.8. So this is the case that correlation is 0, right? Looks like there's no visible, obvious relationship. And this last example is very interesting. X and Y seems to be highly interdependent with each other. You know, there's an obvious pattern between X and Y. Turns out that correlation is 0 in this case. It's interesting. The reason is because correlation measures only linear relationship. So here, this statistical relationship between X and Y is very strong, but the relationship is nonlinear. It's more like quadratic form. It is increasing in the beginning and then decreasing later. So this is nonlinear. And this example is constructed in such a way that this nonlinear relationship cannot be summarized by linear relationship, so that the resulting correlation is always 0. Okay? So that's why even if correlation is 0, we cannot say that those random variables are independent. However, if they're independent, it's always the case that the correlation is 0. Okay? And another important thing is conditional expectation. So conditional expectation of y given x is written in this way in mathematics, in statistics. And the interpretation of this quantity goes like this. So suppose y measures income, annual salary, things like that. And x measures the number of years of schooling. So when x is 12, that means this particular person graduated from high school but didn't study anymore. If x is equal to 6, then this is equivalent to university graduate. In Australia, university is 3 years. So maybe university graduate plus some honor degree or some postgraduate degree. But anyway, a few more years. So suppose we have two groups of people. In the population, suppose, just look at the simple situation. Some people only graduate from high school, and some other people graduated from university. So we can divide this sample into two different groups. One group is this, and the other group is this. Of course, we can have population mean of y, population mean of salary for the entire population. But we know that some people are high school graduate and some other people are university graduate. Presumably, high school graduate may have different expected value of their salary. This salary should be different from the salary that is expected for people who graduate from university. So that is what this conditional expectation is doing. This conditional expectation is expected value for the salary for those people who finish high school only. And this one is expected salary for university graduate. Okay? And then the difference between these two expectations can be interpreted as the effect of university education on annual income under some conditions. So actually this under some conditions, this is very important. We cannot interpret simply this difference as the effect of university education. But we're gonna study we're gonna study first. We're gonna study what are these conditions, and we're gonna study when these conditions are satisfied, and therefore we can interpret this difference as the effect of education. And if these conditions are not satisfied, then we're gonna study how to develop right estimator that capture this effect of university education later. All right. Conditional expectation is very important. In this example, x can take only two values for education, but it shouldn't be like this. Education itself can take any number between like 6 to 16, 20, and many more numbers. In my case, my education, the years of schooling is amazing. It's like, I graduated from university, that is 16 years, and I did master 2 more years, 18 years, and I did PhD for 7 years, so 25 years. So the 7 years it goes like this. I started my PhD at a State University of New York because my wife was going to that university, and I waited. My wife finished her study, and then I started PhD from the very beginning from another university because I wanted to transfer to another university. So that's why I spent 7 years. So anyway, including everything, I spent 25 years as a student at school. So x can take a lot more different values. Actually, x can be a continuous number. And in this course, one of the main objectives is to estimate this conditional expectation as a function of x. And the conditional expectation has another name in statistics. That another name is regression. And if you consider this conditional expectation as a function of x, because for each value of x, you're going to have different conditional expectation. You can say this. You can call it conditional expectation function. Similarly, you can call it regression function. And in real, when the world was created, this conditional expectation can be very complicated function of x. But for simplicity, we will assume that conditional expectation function takes this form. Linear in parameter value, alpha and beta. Linear in alpha and beta. Therefore, this course is going to mostly focus on linear regression problem, right? So we're going to start basic methodologies for linear regression after you guys come back from break, 10-minute break. Let's have 9-minute break. Let's start at 11 o'clock. Sorry for that. Okay. All right. So now we're going to study about linear regression with one regressor. Actually, the textbook says that the textbook take this view that we have one regressor, but from my view, it has to be two regressors. The simplest case is the case where we have two regressors. I'm going to, some textbooks are, in any case, we're gonna start from simple linear regression where we have two terms on the left and on the right hand side. One is constant, and the other one is a random regressor. Some textbooks are counting the constant as one additional regressor. Therefore, I say we have two regressors. But some other textbooks, including this one, counts only random regressor. So, but there's no fundamental difference between these two. The question is how to index this regression function. So basically, we assume that there's a population linear regression model. The model that we saw before, there's a condition expectation that can be written as alpha plus beta times x. So that is population regression. And because that is linear, we can say there's a linear model, right? And using the data, we want to estimate the population linear regression model. So in particular, we're going to study ordinary least squares estimator, which is often called just OLS estimator. And instead of population regression line, we're going to draw sample regression line. So it's just analog to the population mean and sample mean, right? So here we have, instead of just one number, we have a function. So we have population linear function and sample linear function. And in order to learn about the population linear function, using data, we estimate the function that is called the sample linear function. So we will study about OLS estimator, and then we will discuss about measures of fit of the sample regression. After we estimate the linear model, we want to have some measure that says something like, our estimation is good or bad, something like that. So we will discuss about measures of fit. And then we will discuss about some linear square assumptions in order to state more formal results about our estimator. And also, we will discuss about sampling distribution of OLS estimator. Sampling distribution is important because we want to do inference, hypothesis testing, and confidence interval. In order to do inference, we need to have sampling distribution, just like we had a standard normal distribution for sample mean problem. So linear regression lets us estimate the slope of the population regression line. Most cases, we are only interested in the slope parameter. The reason is because the slope can be interpreted in this way. The slope is the expected effect on the left-hand side variable when we are changing the right-hand side variable by 1 unit. So eventually what we want to do is we want to estimate causal effect on y when we change x by 1 unit, just like when we increase the years of schooling by 1 year, what is the effect on the individual's expected salary, something like that. But in order to estimate causal effect accurately, we have to consider some other problems that we are going to discuss in this course. But for now, let's just focus on fitting a line to explain the data. That is the initial point. So basically, the idea is very similar to the estimation of difference between the means between two groups. Average salary for high school graduate and average salary for university graduate. We want to see the difference between these two means. And the idea is just some simple generalization of this kind of estimation, mean difference estimation. But like I said before, the number of groups can be many. So we need to generalize the idea of estimating difference in two different means. So in order to do that, first of all, we have to estimate the line. The line is just a straight line. And whenever you define a straight line, you need to have only two numbers, the intercept and the slope. So basically, using OLS estimator, we're going to estimate the intercept and the slope. That is it. That is what we want to do here, at least in the beginning stage. And once we have OLS estimation, then we will have to discuss what's good about OLS estimate, what is bad about OLS estimate. We will discuss something like that. And just like the example of sample mean, we will have to do hypothesis testing because we know that our estimate is not exactly the same as the population parameters. So using our estimate and using some measure for uncertainty about our estimator, we will conduct hypothesis testing. Especially we are interested in this hypothesis, whether the slope is 0. If the slope is 0, then that's the case that x variable has nothing to do with y variable. So even if we increase or decrease x variable, there wouldn't be any change on y variable. This is an important problem from policy point of view because we want to identify the right control variable in order to achieve some policy objective. We don't want to spend our resource, time, and effort on some variable that has nothing to do with our policy objective. So that's why we want to test this hypothesis. Slope is 0. That means if slope is 0, even when we change the value of x, there will be no change on the y variable, the left-hand side variable. And also confidence intervals. We're going to construct a confidence interval for the slope parameter. We will focus on the slope parameter only. Going back to the example of test score, so we want to see the effect of STR. What was STR? Student-teacher ratio. Student-teacher ratio. This is the example from California school districts from the last lecture. So student-teacher ratio, we want to see the effect of student-teacher ratio on the average test score for year 5 students. And under this linearity assumption, we have two underlying population parameters, beta 0 and beta 1. Beta 1 is the slope parameter, and we want to estimate beta 1 because this measures the effect of student-teacher ratio on test score. Right. The first equation represents the true data generating process. In that sense, beta 1 and beta 0 are population parameters. And we want to know the population values of the slope again. Because we don't know the true value of beta 1, we are going to use this data. And we're going to use the data to estimate, in particular, this equation. This is a population regression line, but when we estimate, we're going to have sample regression line. More generally, the regression equation function can be written in this way. We have left-hand side variable y and x variable on the right-hand side. Let me define one by one like this. I is the index for individual. I is index for individual. 1 means the first observation in our sample, in our data set. And I goes from 1 to n, which indicates that the sample size is little n. And n is the sample size. And we have a random sample of 2 random variables, x and y, across all the observations in the sample. So in the literature, the variable on the right-hand side is called independent variable or regressor. I prefer the last one, right-hand side variable. If we call it right-hand side variable, then the location of the variable is so obvious. It's right-hand side, right? But traditionally, it's been called independent variable, and sometimes regressors. Actually, many times it is called regressor. But I don't like the first name, independent variable, because in many cases, the regressors are not independent at all. When you call x as independent variable, then y is going to be dependent variable. But I prefer this new name, left-hand side variable. Again, when we call y as a left-hand side variable, then the locations become so obvious, so clear. Beta naught intercept and beta 1 slope. So these two are population parameters that we want to estimate using the data. And ui is a regression error, or just error, or prediction error. So depending on the textbook that you are reading, or depending on the paper that you are reading, the name for this last term can be different. Error, regression error, or prediction error. What is the role of this error term? Error term may include many different factors that are not included in this simple equation. When we explain y, we could have x, but we may have a lot more other things. Or x variables can be measured with some measurement error. Y variable as well. When we collect sample, people can make some error. So there can be some measurement error. All those measurement errors are included in this last term, error term. And back in the school test score example, so we want to have test score on the left-hand side variable and student-teacher ratio on the right-hand side. In that example, test score is going to be determined not only by student-teacher ratio, but also by so many other things, like average education level for parents in the school district, right? Maybe your parents are more educated, then your parents are more interested in you guys' education. Therefore, they will push you to study harder. Then obviously, if a certain district parents are more educated, then it's likely that their average test score will be higher than other districts with parents with lower education level. Similarly, parents' income level may affect students' test score. There could be so many other elements that determine test score. So when we write the test score as a function of student-teacher ratio, then this U will collect all other things. Actually, the relationship between error and the regressor that is included in this equation will play a very important role when we try to estimate the parameters consistently. We will discuss about that issue later. So here, this is an example of population parameter, population regression function. we don't know. So, this is our assumption. We have population parameter. So the creator of the world draw a line just like this. And then the error terms are error terms are coming from some distribution. Therefore, it determines the locations of the dot point. The dot points are not going to be on the line exactly because of the error term. This relationship is a statistical relationship, stochastic relationship. It's not deterministic relationship. Because of the error, there's a difference between the locations of the dot point and the population line. So this is tricky part. Using scattered data, we want to identify and estimate this one straight line. Again, this is an example, and this is a hypothesis situation where we know the population regression line. We don't know the line. That's why we need the data to estimate the shape of the line, location, and the slope of the line. Okay? So if we estimate beta naught and beta 1 using data, then that is estimation of the population regression function. The way we are doing is very similar to solve this minimization problem. Refresh your memory about what we discussed about last time. We are using sample mean because sample mean solves this optimization problem. We choose one number that explains the sample the best. What we mean by the best, you can think about this expression. So by choosing one number m, we want to predict random variable y. And because y is random variable, we're going to make some mistake. Our guess is going to be different from the random variable itself. So we take the difference and then we make it positive by raising power 2, and then we take summation, and this is sample mean squared error. So sum of mean squared error. So we want to minimize our cumulative error by choosing some m. When we solve this optimization problem, the solution turns out to be sample mean. And sample mean, using sample mean, we want to estimate the population mean. So our objective function for linear regression problem is very similar to this estimation of mean problem. So here, x is supposed to be informative about y. So using this information, we want to estimate the random variable y. And we specify the relationship in this way, the linear. So instead of choosing one number, we're going to choose two numbers, b0 and b1. This is a b1. This is not bi. So if you solve this minimization problem with respect to b0 and b1, then that becomes the solution, which is called OLS estimator. And by doing that, we are estimating this population conditional expectation function. So let's look at the data once again. Data for the test score and student-teacher ratio looks like this. This is a scattered diagram. Okay, and the idea is we want to draw just one straight line that explains this scatter diagram the best. This is tough task because these dots are widely scattered, and we are restricted to draw just one straight line to explain the relationship between student-teacher ratio and test score. But we have data, and by solving this minimization problem, we can choose our estimate for beta naught and beta 1. So, so the minimization problem can be solved by using some calculus. We are not going to do that. If you are interested in, then you can look at the textbook. And the resulting solution is called OLS estimators of the intercept and the slope. And this is a formula for the OLS estimator. We find the slope estimator first, and the slope estimator looks like this. And once we have slope estimator, then the intercept, our OLS estimator for the intercept is defined in this way. We take the average of y variable and average of x variable, and then multiply this average of x variable by our OLS estimator for the slope parameter. So from this expression, it's pretty obvious that OLS regression line goes through sample average of x and sample average of y. But that is one side point, which can be important. But I don't want to emphasize that. Maybe I don't want to emphasize that because that is too obvious. Using this second equation, it's pretty obvious that regression line goes through the sample mean and sample average, right? And the slope parameter, the formula, I don't want you to memorize this formula. The first reason is because formula seems to be pretty complicated. And second, in the real world, we are not going to use very simple linear regression like this. Most of cases, we're going to have many random variables on the right-hand side, not just one random variable. If you have more than one random variable on the right-hand side, then the formula is going to be a lot more complicated than this. So, memorizing this formula for one very particular case doesn't help you to do anything. So that is the reason why I don't want to memorize this. However, it's good to see what's in this expression. If you divide both numerator and the denominator, then what is going to be the numerator? So you have this numerator, sum of product of mean deviations, and divided by sample size n. That is sample covariance between x and y, right? So there's an interpretation for what we see over here. So I want you to have the interpretation. And denominator, this is mean deviation, sample mean deviation, power 2. So, sample mean deviation square, and sum of it. This, if you divide this denominator by sample size, then that is sample variance, right? So when we have only one random variable on the right-hand side, then the slope parameter has obvious, very clear interpretation. That is ratio of sample covariance to sample variance of regressor, right? Then it may be easier to remember. Once you remember this interpretation, then you can write down the math like this. If you know the definition of sample covariance and sample variance. Now, one of the reasons that we want to estimate this OLS estimator is because when we have new value of x, we want to predict the left-hand side variable. So suppose xi. So now here, we are using some random variable that we observe in our sample. So when we evaluate this left-hand side at some x value y, then we have predicted y value or fitted value of y. And the notation for that is a y hat. So here we put hat whenever the thing is estimated or predicted, right? So beta hat is estimator that we compute using the sample. when you don't have a hat, then that is unknown population parameter. So you have to make a distinction. What is estimated thing and what is unknown thing that we want to estimate. So when we put hat, that is estimated thing or predicted one. And the difference between the true random variable and our prediction is residual, U hat. U hat is different from error. So let me go back to error. So in this slide, U is part of the population relationship. So U is population quantity. You don't know U. From the data, you cannot, if you know U, then that is not error anymore. U is something that you cannot observe or compute. But U hat is different. Once you estimate the OLS estimators, then you can construct the fitted value of Y, and the difference between actual value Y and the fitted value of Y is defined to be residual. We are using similar notation, but U hat is very different from just U. You have to make distinction between U and U hat. Okay? All right. You know, everything that with hat can be computed by our sample. That is important. Using this, we want to estimate unknown population parameters beta naught and beta 1. So we have data, and using the data, we estimate the population regression line. So our estimated regression line looks like this. The slope is a little bit negative, and it has intercept around close to 700. Over here we have number 698, and the slope is negative 2.3. So using data, we can figure out the intercept and the slope using the data. So therefore, this is our estimate. And in the sample, we have one observation with a student-teacher ratio of 19.33 and test score 657.8. So when we compute the predicted value for test score, we use just this formula. Then the predicted value turns out to be 654.8. And this difference is a residual. So residual turns out to be 3. This observation should be somewhere over here. So because STR is close to 20 but below 20, so it must be somewhere over here. One of these dots is this point, 19.33 and 657.8, one of these dots. And that dot, the residual, is 3. Okay. During the tutorial, we are going to use Stata, and using the data that you see graphically over here, if you run the regression, then this is the computer outcome. So, so let me explain just a little bit. So regress is the command for regression. This is a command of Stata. And the first variable, so after this command, you have to list the variables that you want to analyze with space between variable and after the command. The first variable is left-hand side variable, the dependent variable. And the second variable, or if you have more variables, you need to list all those regressors after the dependent variable. So test score and STR is student-teacher ratio. And after comma, we put robust. This is an option. If you do not put robust, then Stata will assume that the distribution for every individual has the same variance, we're going to discuss about that. But in economic data analysis, that additional assumption is not reasonable. So we want to have robust option. By doing this robust option, we will have robust standard error. And when we have robust standard error, our inference is going to be robust with respect to some problem. We are going to discuss about that problem later. And this is the line that you type in your computer, the first line. And then if you hit the enter key, then the computer will give you the rest of this table. Not this one, but up to this last dashed line. So regression with robust standard errors, this is what this computer is doing. And the result is summarized like this. And number of observations is 420. And we're going to explain, we're going to learn what these things are soon, later. And I want to focus on this highlighted part. The coefficient that is attached to this regressor is estimated to be negative 2.28. And the coefficient for constant, which is intercept, that is estimated to be 698. So in the regression equation, in the equation form, we can rewrite this result in this way. Okay? So far, we learned how to read the first column of the computer outcome, of the state outcome. And using this first column, we can rewrite the estimation results in this way. So we're going to discuss everything else later. So two regression statistics provide complementary measures of how well the regression line fits or explain the data. We're going to discuss about two measures of fit. One is R-square, and the other one is standard error of the regression. Let me give you the definition of R-square first. In order to define R-square, we need to be able to calculate variance of random variables. We all know how to calculate sample variance. This is the variance of left-hand side variable, sample variance. You know, sometimes people divide it by n-1 to take care of the degree of freedom. But let's forget about that. You know, the sample, you know, dividing it by n or dividing by n-1, they all become similar when n is large. So for now, let's say we're going to divide this summation by the sample size. And sample variance of fitted value y hat, the explained part, we will have the same formula, but the random variable is y hat instead of just y. And we're going to have sample mean of y hat. And using this expression, we can calculate sample variance of y hat. Because the regression line goes through the sample mean point, turns out that sample mean of the predicted value is exactly the same as sample mean of y. So sometimes we can use y bar instead of y hat bar because they are the same. Numerically, we can prove this result. R square is simply the ratio of second sample variance to the first sample variance. And the interpretation is this. This variation is explained variation because when we calculate this sample variation, we used our predicted number, not the actual number, actual random variable. So the numerator is variation of explained part. Or people call it explained sum of squares because this sum is the sum of squares. And the denominator is variation of the left-hand side variable, the left-hand side variable itself. So this is total sum of squares, or total variation of the random variable that we are interested in. So this ratio is the definition of R square. Turns out that there's equivalent definition. Sometimes you have sum of residual squares. If you have sum of residual squares, then 1 minus this ratio is equal to the ratio of explained sum of squares and total sum of squares. So these two definitions are equivalent. Numerically the same. You're going to have exactly the same number. If R squared is 0, then that is the case that this numerator is 0. So your regression function your sample regression doesn't explain anything about the left-hand side variable. So there's no explained part. If R squared is 1, then these two sample variations are exactly the same, which means this straight line explains all your data point, which means data are generated from deterministic relationship, which is not common, right? So most cases, actually, essentially almost, all the cases, your R squared is going to be between 0 and 1. If R squared is closer to 1, then your regression, estimated regression lines, your estimated line is doing a good job to explain your data. If R squared is closer to 0, then your regression doesn't have good prediction power. Okay. Alternative measure for goodness of fit is standard error of the regression. So here, this is just definition of standard error, and we take into account the degree of freedom. So instead of dividing the sum by the sample size, we are subtracting 2, because in this problem, the number of parameters is 2. So we fix 2 points. When you draw the regression line, you need to have at least 2 points, right? So you are losing degree of freedom. So that's why you divide it by n minus 2. And this is the definition of SER. The definition is so simple. Just once you have residual, then just calculate the standard deviation of the residual, taking into account the degree of freedom. And as you see over here, going back to the R square, all R squares are between 0 and 1. Just like this, there's a determined interval, 0 and 1 in this case. And it doesn't depend on the unit for your data. Whether things are measured by dollar, whether things are measured by cents, it doesn't matter. R square is unit free. It doesn't depend on the choice of unit. But here, this is standard error. If you remember the fitted value here, yeah, right. So, so when y is measured by dollar, then it has to be that the residual has to be measured by dollar as well, right? So the standard error of regression is unit specific. So depending on the unit of left-hand side variable, you will have different unit for SER. Alternative measure is basically root mean squared error, or RMSE. Everything is the same, but you ignore the degree of freedom. When you have large sample, RMSE is the same as SER, so there's no distinction between these two. So, if you look at the computer outcome like this, you can find R square over here on the top right corner. R square turns out to be very small, 0.05, which means, roughly speaking, this is very close to 0. This regression line doesn't do a very good job to explain the data. And RMSE is standard deviation of residuals. That turns out to be 18.581. And the unit for this is the same as the unit for the test score. Where is... the Stata doesn't report SER. It reports only RMSE, root mean square error. But because sample size is large, in this example, sample size is 420. So we can assume that SER should be very close to root mean squared error. Right, so R square is 0.05 and SER is 18.6 because it should be very close to root mean error square. Yeah, because R square is very small, we can say that STR explains only a very small fraction of the variation in the test score. Does this make sense? I'll say it makes sense because, like we discussed before, this is too simplified. The test score can be determined by many other elements. So later we are going to include additional regressors to increase the fit of the estimation. And does this mean STR is not important in policy sense? We don't know about this. Actually, it does not mean so because in order to answer to this question, we need to have a proper regression equation. This regression equation is too simplified again. We have to control for additional factors to answer this question. Okay? Right. Okay, so now we will have to discuss about least square assumptions. Under some assumptions, before making any assumptions, so far what assumption did we make? We made one assumption, that is the population regression line is linear, right? So far we only made linearity assumption. But only that assumption by itself doesn't allow us to say something like whether our estimators are good or bad. More specifically, we cannot even say whether our OLS estimator is unbiased or it is efficient, something like that. So in order to study the statistical property of OLS estimator, we need to make some additional assumptions. For now, I'm going to introduce 3 additional assumptions, and we're going to call them as least square assumptions. The first one is when we write down the regression line in this way, the conditional expectation of error is 0. Which means this conditional expectation, mean 0 assumption, the first one, that implies that error term is not correlated with regressor that we have in our data. There's no correlation between X and Y. 0 correlation is implied by this 0 mean assumption. So one way to think about this is knowing some particular characteristic of the observation doesn't give you any information about the magnitude of the error term. So suppose you know that individual is high school graduate. This information doesn't allow you to say that the error term is going to be positive no matter what. You cannot say that. The error term is going to be 0. So the information contained in regressor has no information about the error term. Knowing student-teacher ratio for a certain district doesn't have any information about the omitted factors. So that is conveyed by this assumption. That is a really important assumption. Later, we're going to use this assumption for consistency of OLS estimator. And also, under this assumption, we can show that OLS estimators are unbiased. Without having this assumption, we cannot even say that OLS estimator is unbiased. And the second assumption is this data for each individual is actually random sample. These are coming from the same underlying distribution, and they are all independent with each other. And this is true if the data collection is really random sampling. And under this assumption, we can develop the theory for sampling distribution of OLS estimators. Under some situations, this assumption is not satisfied. For example, if you have time series data, then I index time. For some I, it's 2019, and then I plus 1 is going to be 2020. I minus 1 is going to be 2018. So many variables are serially correlated in this case. GDP this year is highly correlated with the GDP last year. So when you have time series data, then this second assumption is not satisfied. And number 3, there's no outliers in both X and Y. This is very, so outlier assumption can be stated in more technical form, but just remember that, this can be rewritten mathematically, like, expectation of X power to 4 is finite, and expectation of Y power to 4 is finite. That can be replaced. That can replace this third assumption. So the reason is because when you have outlier, then it may change the OLS estimator drastically. So the first assumption, for each. So when you have population regression equation like this, the Y is going to be distributed in this way. Especially, you need to notice that the center point of the Y distribution is exactly middle, and the location is on the regression line. So the regression line goes through the center point of the distribution of Y variable for each possible point of X. And we're going to spend much time on discussion about whether this assumption is plausible in our given situations. I find that we are running out of time, so I cannot finish these assumptions. So let's start discussing about this linear least square assumptions next time. And after finishing this part, we're going to start talking about inference for simple linear regression. All right, so let's stop here, and I will see you next week. Have a great week, and I'll see you next week. Delete. No. How to log out? Question?
Check if a blue water bottle was found here last lecture.
No.
It's my brother's. He's had to go to work, but he wasn't sure if he left it blue.
No, I didn't find.
No,
Yeah, sorry. Question?
About the
Are you the lecturer for the psychology course?
I am.
Yep. Would you mind if I gave just an announcement about the climate strike happening next week? Sure. Okay, awesome. I was here last week, wasn't I?
You were.
Yes.
That's all right. Have you targeted? To not many people say yes.
Yeah, no.
Kidding. That's all right. I don't mind.
Yeah, no. Yeah, sometimes.
All right, let's get started.